introduced. Yeah.
Yeah. You go ahead.
Good. Yeah. So thanks very much. Thanks to the organizers for inviting me. It's a pleasure to be here. Very nice workshop. And I realized that the title of it is Topological Materials and Beyond. And I think we heard a lot about topological materials so far. So I thought I might try and see what can be done in the beyond category. This talk is really, as the last talk in the workshop, meant to emphasize that that there's this delightfully nondescript notion of beyond. All right, so I'll talk about many-body band inversions, and the case that I want to make is that there is a special class of band inversions for which you would expect interactions to be important. And these provide an interesting new venue for strongly correlated electrons to exhibit unconventional and new, possibly exotic versions of collective behavior. And so this is in part motivated by the fact that the notion of band inversions has been very powerful in our understanding of topological phases, in particular free fermion topological phases. And at the same time, it's also given a very useful prescription to look for materials that might realize topological phases. And so we were motivated in part by the question, does there exist some notion of a many-body generalization of this band inversion transition? And so what we realized, and what I'll try to argue, is that this requires a special class of band inversions, which we call higher angular momentum band inversions, for which interactions are expected to determine the fate of the transition. And so in this talk, I'll basically introduce that, and I'll also discuss some lattice models that would realize these higher angular momentum band inversions, which might then point to at least some routes of possible realizations. And in addition to introducing a wave function for an exotic phase that you might expect at these higher angular momentum band inversions, I'll also talk a little bit about some field theory results of interactions in these systems. So this is work done while I was still at Penn with Yishen Hu and Charles Kane, and these are the references. So hence the Penn is meant to indicate that most of the work was pretty much all the work was done there so far. Okay, so let me start by just beginning with the notion of a band inversion and take the simplest case, which is the transition to a Chern insulator in 2 dimensions. So that involves 2 non-degenerate bands. And so here on the left side would be the uninverted case, and on the right side here, this is good, yeah. On the right side here is the inverted case, and that would realize the Chern insulating phase. And so you can parameterize this band inversion by a mass or a band inversion parameter, which I here call delta. So when delta is positive, delta just measures the energy difference between the bands of these 2 states. And if it's positive, and you fill this band completely, you just have a real band insulator. And here, delta has switched sign, and that describes the Chern insulator. When delta is 0, you're right at the transition, and then the system is gapless. And this gapless point is, as we perhaps know very well, described by a Dirac fermion with linear dispersion. So that implies that this is an example of an angular momentum 1 band inversion. And it furthermore implies that the density of states right at the transition vanishes. In contrast, higher angular momentum band inversions are band inversions between bands which have relative angular momentum larger than 1, where L labels the angular momentum. So in that case, the situation is very similar. So you have the uninverted case here, which describes the trivial phase, and here is the topological phase. And in this case, the band inversion describes the transition between a trivial phase and a phase with higher Chern number. So that's on the right side. But now in this case, the critical point right at the transition is also gapless, but the dispersion is not linear but quadratic. And that implies that the density of states is non-vanishing. So then you would expect perhaps that right at the transition, interactions would do something to it. And so here I want to propose such type of band inversions as a venue for correlated physics, and more broadly propose that it might be a new paradigm for studying interacting phases, and in particular topological interacting phases, beyond the flat band paradigm, which in the next slide I'll argue is sort of the opposite limit of the band inversion paradigm. So in particular, I'll talk about two possibilities for correlated behavior. One exotic, which is a fractionalized correlated fluid of electrons and holes. And I would argue that this state is akin to a Laughlin state, and the essence of our proposal is a many-body wave function that should describe this phase. And what would be interesting about it is that this is a Laughlin state, meaning a fractional clone Hall state at zero magnetic field, and perhaps more importantly that it would happen at stoichiometric band filling, because you're doing this in the context of a band inversion rather than a fractionally filled band. So this first thing has been famously shown that magnetic field is not actually a requirement, but perhaps this might also help you with that complication. And the second thing that I'll talk about is just a more mundane or less exotic symmetry breaking transition, and that involves a pairing of electrons and holes. So you might call this exctonic pairing, which form a condensate, and that the symmetry that is broken is rotation symmetry, and I'll discuss this. So as I said, one of the main things that I'd like to showcase is that in particular this type of physics can come out of a paradigm that is very different from the paradigm that we're used to in describing strongly correlated topological phases, and that is the flat band paradigm. And the canonical example of that is the case of Landau levels and the quantum Hall effect. So in a two-dimensional electron gas in a perpendicular magnetic field, the energy levels reorganize into these flat Landau levels, and because of the structure of these Landau levels, it's possible, famously proposed by Laughlin, to write down a many-body wave function for the fractional quantum Hall state that has been observed at fractional filling of one of these Landau levels. And the physical consequence of that is this quantization of the Hall conductance in fractions of p squared over h. And so, because of this special structure of this Landau level spectrum and the states of a Landau level, you can make progress with these many-body wave functions in this way, where here, just to set the stage for what is to come, where the zi and zj are complex coordinates of the particles, I and j label the particles, and m here is this exponent, which is 1, 3, or 5, which are these Laughlin series, and as such, it's become a sort of flat band paradigm for strongly correlated topological phases. And what I would like to do is sort of propose that similar things can happen in the band inversion paradigm. So let me move to that again and begin by first considering the simple case of the transition to just a Chern insulator. And in order to do that, what I'll find convenient is to rephrase this problem in terms of electrons and holes. So what I will do is I'll say that the creation of a hole is equal to annihilating a state in the valence band, and so those are holes, and electrons, that is just creating a state in the conduction band is just creating an electron. So in doing this transformation, that means that the coupling between the bands takes this form in terms of electron and hole pairs, and this function delta of k here now describes the structure of this coupling. And so you might call this some type of since you're pairing electrons and holes, you might think of this delta describing some form of exctonic pairing, but it should be emphasized here that this delta does not reflect a symmetry breaking, so this term is present present in the Hamiltonian. So one should be a little bit careful with really calling it a pairing. So with that, let me then describe Hamiltonian for these type of band inversions. And so I'll actually move here for a second so that I can see the slides. So the Hamiltonian takes this 2x2 form because we're talking about two non-degenerate bands, and so on the diagonal is just the dispersion, the quadratic dispersion of the bands, and the band inversion parameter, which measures the difference between the bands, and on the off diagonal is the coupling between the bands, and this off diagonal coupling takes the form written here, where L labels the angular momentum. So this is why where the name higher angular momentum band inversion comes from. And so let me begin by first considering the case L equals 1. So that is a model for transition to a Chern insulator. And what I would like to do is get to a wave function. So in order to do that, you can invoke the work done by Reed and Green, where they formulated a ground state wave function for this in terms of in their case, for a P plus IP superconductor, for for this case here, in terms of a BCS wave function. So then you just obtain this BCS form where now this G of K encodes the angular momentum. So in the case of L equals 1, it sort of describes this P plus IP excitonic type pairing of electron and hole pairs. So going to real space, so Fourier transforming, we would like to have a wave function in terms of the coordinates of the particles and the holes. So I'm going to work towards a wave function for n electrons at position Zi, where Zi again are the complex coordinates, and n holes at Wj, and W are the complex coordinates of the holes. So in the topological, in the band inverted case, the Fourier transform of G of K is given by G of Z, which is 1 over Z. And it's actually possible to write down a model, or a Hamiltonian, shown in the previous slide, such that at a particular point of this model, this is exact. And so then you can proceed by just working out what that wave function should be by taking the many-body wave function as the determinant of this G of Zi minus Wj. And if you use this, then what you obtain is this form here shown on the right-hand side. So that already shows you that it's a little bit similar to what I've shown before. So it's the coordinates of the particles, of the holes here, and their difference. And here is the coordinates of the particles and the coordinates of the holes. And so the way in which one might think about that is an angular momentum 1 pairing of electrons and holes, and so that's why they're in the denominator here. And so that you could establish really exactly for a particular free fermion model for the case L equals 1. And so I want to take that and consider a wave function for the case where L is 3 or other odd numbers. And so to do that, I'll contrast again these two different paradigms. So the flat band paradigm, where we have electrons in the magnetic field, so the Landau level problem, and the band inversion paradigm, where you have electrons and holes. And so in case of the nu equals 1 state, then this would be the well-known wave function for filled Landau level. And here you would notice first that the particles are in a relative angular momentum 1 state. And in this wave function here, which describes the Chern insulator, you would note that in the denominator here, the electrons and holes kind of are in a relative angular momentum 1 paired phase. And so you might think, well, let me then take this wave function here, where m is 3 or any other number, and generalize that, and just similarly here, take the power to the angular momentum L. And so this then constitutes a proposal, an idea, that a wave function of this form might describe a strongly correlated phase, which is akin and has the same phenomenological properties as a state described by this wave function here. And the name we gave that then is the fractional excitonic insulator. And so I want to talk about this wave function a little bit more because here it's just presented as a proposal, which it is. But there are a number of pieces of evidence that we've thought about that might give confidence that such a state is. Question?
So without the Gaussian factor, the wave function is normalizable or not?
Yeah. So So because in the L equals 1 case, it just came out of the starting point was a wave function that was normalized, and then you just pull it out of that. But you make a good point that the difference between these two was, of course, the fact that the magnetic field is absent, so the Gaussian factor is absent in the band inversion case. And so there's three things that I just want to mention here, and then I'll talk a little bit more about the third one here. So what's been very powerful in the case of Laughlin wave function and the quantum Hall effect is a plasma analogy, where you interpret the wave function squared as the partition function of the plasma. And one can do something similar here, where you essentially recover the Kostelis-Thouless problem of vortices and anti-vortices, which here then become the particles and holes, and show that there's a plasma screening phase, which then gives confidence that perhaps there is an incompressible fractional quantum Hall state described by that wave function. And another route we explored was is a composite fermion model, where you go to different degrees of freedom, the composite fermions, meaning the composite electrons and composite holes, and by flux attachment, and consider a mean field state for the composite fermions. And in that case, one can show that the response, meaning the Hall conductance, is also quantized in fractions of p squared over h. And the third one is the idea that you might try to derive a Hamiltonian for which the wave function you propose is an exact ground state. So that's the idea behind that is sort of seeking an exact question to the answer, where the answer is the wave function, and you're trying to find the exact question, which is the Hamiltonian, which is also that's also lifted from ideas that have proven very powerful in quantum Hall physics. And so the idea here is that I'll go here again. That the starting point is to seek an operator, which here is called Q for you do this for both electrons and the holes, such that this operator annihilates the wave function. And so it ends up having this form, and then if you find that, then the wave function is a ground state of this Hamiltonian. Now, so the form is pretty complicated, and so is this Hamiltonian. But there's two things I want to note. One is that the Hamiltonian you derive based on the general many-body wave function. If you choose L equals 1, then you exactly recover the Hamiltonian of the non-interacting problem that I sort of started with, and that describes the transition to a Chern insulator. For L equals larger than 1, the Hamiltonian involves many-body interactions, so it becomes very complicated. But there's one thing and that's why I want to talk a little bit about the exact Hamiltonian that's interesting about this, because what you can do is you can take that Hamiltonian, which has these very many-body interactions, and you can switch off the interactions, and then ask the question, what Hamiltonian do you get? And it turns out that you get the following Hamiltonian for the electrons and the whole degrees of freedom, where epsilon of k now is just k squared. So that's similar to what we had before, except that delta is exactly equal to 0. And the coupling between the electron and Hall degrees of freedom is given precisely by this higher angular momentum form. So that inspires confidence that these higher angular momentum band inversions are indeed a promising venue to look for this. And the idea that we have is that if you take such a Hamiltonian and introduce some physically sensible interactions, that that you may still recover a ground state that is described by the wave function. And so since this coming from this exact Hamiltonian shows that higher angular momentum band inversions play an important role. Okay, I'll speed up a little bit then. Play an important role. I want to ask the question: where might one find these higher angular momentum band inversions? How can we realize these? What materials might have that? And in order to do that, I want to ask the question: what Hamiltonian, non-interacting Hamiltonian, has these higher angular momentum band inversions, and in what case are they protected? Is this a protected feature of the system? And so then you look at the symmetries and the symmetry quantum numbers, and in particular you have to look at what are the symmetries of an angular momentum, because we're talking about an angular momentum here. So it's certainly odd under mirror reflection, but it's invariant under rotations, and actually rotations turn out to be very important, because rotations are the symmetries that allow us to distinguish angular momentum. And in a lattice, we only have n-fold rotations, where n is up to 6. And so if we want to distinguish angular momenta, then we realize that 6-fold symmetry is ideal, because that's the maximum rotation symmetry that you can get. So in the rest, in the models that I'll describe, I'll focus on 6-fold rotation symmetric systems. And so another thing you need is that in order to have this higher angular momentum band inversion, that this band inversion is between bands that have the right relative angular momentum quantum numbers. So there's 3 basic ways in which one can do this. One is to consider cases where the bands are described by different atomic orbitals, have character of different atomic orbitals, or perhaps in spin-over coupled systems you can think of spin, where spin 3½ and spin -3½ band. They also have a relative angular momentum 3. If they invert, that will lead to the same system. And a third case, which is kind of important also to mention, is that this can come from structure in the unit cell. So here in this simple structure here, you can form states that are bonding and anti-bonding states of the 2 sites, and one will transform as an S-wave state, and another will transform as an F-wave state. And I'll talk about a model that does this. And so based on these sort of ideas, we introduced different classes of model Hamiltonians that at least give some idea of where to look for realizing these types of band inversions in materials. So I'll discuss 2 just to give you an idea. So one is a model on a triangular lattice with S and F wave orbitals. So on each site you have an S and an F wave state, and then they couple to each other by these F wave harmonics. So this is a picture of how you couple the states. So this is parameters of the tight binding model. And what you see from this is if you go around, then this has the symmetry of an angular momentum 3. Another example is a honeycomb lattice model also, as Eslam noted this morning, already has the C6 symmetry. And in that case, it's actually pretty simple. Most of you will probably know this, that you can, with the Haldane prescription, realize a Chern insulator. But if you also introduce a third nearest neighbor coupling, so this T prime here that goes across the hexagons, then what you're able to do is at gamma engineer a band inversion between states that have effective S-wave character and effective F-wave character. So with this additional parameter, even the Haldane model can realize an angular momentum 3 band inversion. And so the spectrum of that looks very simple, just like this. It's pretty easy. And here I show the The inverted case where there's a small gap here, and it's pretty small because the coupling is cubic, so that makes this gap small. But so with these models, you know, it's first of all it gives some idea of where to look for materials. At the same time, you may use them to numerically test some of the ideas that we put out here. So how much time do I have?
0.
0. Okay. So then I guess I had some stuff on mean field theory, but I'll just leave it at that then and put up the some concluding remarks, and thank you.
Are there any questions, the audience?
So in this state for the fractionalized excitonic insulator, do you construct this exact parent Hamiltonian as like a positive definite operator of which the excitonic insulator is an exact zero energy ground state? Like, do you know whether this is the only zero energy ground state, or whether there might be a larger ground state degeneracy or even
No,
extension?
so we don't know that, and we don't even know that the Hamiltonian has a gap. So far we only established that this is that it annihilates, that these operators annihilate the wave function, so that it is a ground state or a zero energy state. But no.
Why don't you know the Hamiltonian has a gap? Have you done numerics?
No, we haven't done numerics yet.
Why?
we didn't do it yet. We haven't gotten to it yet. But I mean,
Seems kind of important to establish if it's got a gap.
yeah, I mean, sure, yeah. But that's to be done.
So one thing I was just confused about is you're talking about phase transitions, which are semi-metals, and then also talking about like starting with an insulating phase, which was a band inversion. Like, is this an instability of a small gap insulator, or an instability of a semi-metal with a quadratic or higher order dispersion?
So I guess what you're asking is whether or not this is expected only right at the transition, or a little bit. How far do you have to be away from the transition?
Yeah, or if it's not a transition, if we're starting from just a semi-metallic phase that's pinned by symmetry, is it instability of that phase? So instead of having electron hole bands, you just have a semi-metal.
I guess I'm wondering in what sense do you mean semi-metal, as in just
Like a
gapless point that has to be.
Yeah, a symmetry pinned quadratically dispersed.
Oh,
gapless point.
okay. It's possible, but I mean in this case, the symmetry required might be a bit different because in the presumably it's the pinned because of some symmetries that I would require to be broken.
Yeah, broken by the many-body interaction.
It could be, yeah, it could be.
That's exactly what I was thinking of.
Yeah.
It would be that instability of, you'd start with a semi-metal,
Yeah.
the interacting term would gap it. Yeah.
Yeah. So in the L equals 3 case, one can
Yeah.
think of the ABC stacked trilayer graphene, which has this the cubic touching points. So
Yeah.
it's yeah.
Okay, because maybe that could be a place to look, because now they
It
have
could be,
these,
yeah.
huge database of materials with certain Europe's at certain points, and certain of them will have these specific dispersing.
Yeah, no, that's yeah.
Any other questions? I have one last one. So you're saying this perhaps points to materializations, and your reference to the Haldane model. Like when you see this quadratic touching point, immediately you can think about terms of tri-layer graphene as a possible system. Is that something where you can see an avenue how to realize that concept?
But the quadratic touching is that's not the only thing that you need. You also need the higher elemental coupling between the bands. So and the quadratic touching here only is happening right at the transition. So it's not So the thing is, quadratic touching. Maybe another way of phrasing the question is what would happen at L equals 2, because I've kind of sort of always as far as which I didn't discuss, the mean field theory is concerned, the answer is yeah, that might similarly be very interesting to look at. As far as strongly interacting stuff is concerned, I don't know yet. Yeah, it's I think
All right, then that's it. Let's close the session. Thank Jörn and all the other speakers again.